Thank you, Andes, for the invitation. Thank you, Linley, for the primer, the mathematical primer on how AI technology works. Let's look at the applied aspects of AI, how to actually put it to use, and look at how to make it more efficient when you deploy AI at scale. And please excuse the matrix pun. Why inference? For the better part of last decade, decade and a half, the technology has been in a stage of proving. It was all governed by training. Who has the best model? Who can run image search? Who can answer better questions? Something flipped around 5 years ago. And now we're in a stage, as we just heard, where it's no longer about who has the biggest model or who has the most data. It's about who can serve more users, who can serve more complex applications, and do so while being profitable. Now, that last bit is not quite done. That said, inference itself has evolved from, say, a single-turn chatbot-like application to multi-turn, more complex use cases to entire ensembles of agentic workflows that companies are deploying. What that means is the technology really works now, up to a point where it's getting a rare thumbs up from someone like Andre. And we see that also reflected in the run rate of revenue for companies like Anthropic, which is growing at a staggering 10x rate every year, while not being profitable. That second piece is what governs us, takes us to the second trend, which is that there is an appetite in the industry for looking at alternative architectures. Even NVIDIA recognizes that AI technology, which has been growing together with GPUs, cannot do that anymore. They need something other than GPUs to reliably and scalably deploy AI. And we see that in other places through our partnership, as well as the partnership between OpenAI and Cerebras. So let's look a little closer at what really makes AI computing so different and difficult. Let's start with some observations. And again, these will resonate with what we learned from Linley. First one is about the hardware itself. There was a question about, do teraflops translate to performance? No, they don't. For AI applications, they don't always translate to performance alone. There are several other things that have to be solved together. Now, also, we talked about matrix multiplications, but that's not what LLMs are doing all the time. They're doing that a lot, but not all. Another thing is models are evolving. They are not set in stone or etched in silicon. Finally, we are going to talk about chips. Several of us are going to talk about chips, but AI computing is a systems problem that doesn't get solved by a chip alone. So with those observations, what do? We optimize for bottlenecks where they exist in the hardware. So it's not just compute, but everything else around it. We have to provision for not just matrix operations, but for everything else, which is the transcendentals, the dynamic paths, the nonlinear operations. As we learned, models are evolving. So we have to make sure the hardware is not a one-trick pony. It has to be programmable. And finally, let's design together with software and systems so that it's a systems problem and solution. Let's look at just one such bottleneck corresponding to the first observation. Where is the inefficiency in LLM inference coming from? It won't be very surprising that during the decode phase of LLM inference, it's all about data movement. You're moving a ton of model parameters and caches from memory down to the computing engines and doing a tiny bit of processing with it. What that means is that your arithmetic intensity of the model is so low that your hardware is sitting there idle. It's a glorified memory controller, for all you know. The typical trick in situations like this is to go to a higher batch. You amortize the cost of weight movement or parameter movement by doing more computation for the same amount of data fetch. Unfortunately, that trick doesn't work with LLMs, because with higher batch, you get even more data movement because the cache keeps on growing. So if you look at any of these curves corresponding to the models, they will flatline after a certain low batch, around 30, 64, or something to that effect. If you have a hardware architecture whose native arithmetic intensity does not intersect any of these models, you can never utilize that hardware well. So just a quick teaser, the green line is our arithmetic intensity. So we should be able to do well. We'll see. What about the GPUs? They're certainly not on this graph. They're probably not even on this slide, somewhere in the roof, maybe. And it's not just our observation. Bill Daly said the same thing a few weeks ago at GTC. The data movement is the single biggest bottleneck affecting AI computing. Two key numbers that I would like to point out from this slide is, just remember, 4 terabytes per second and 4 picojoules per bit. We'll come back to it. But what that means is, if your data movement is the problem, you cannot arbitrarily increase the memory bandwidth by brute force because of the 4 picojoule per bit. If you were to increase the bandwidth of HBM by 10 times, you incur 10 times the energy cost of doing so. We shouldn't be doing that, right? But that's really what is happening. If you see the CAGR at which the server designs from NVIDIA are growing, it's following an ugly form of Moore's law. Every 2 years, the power density of those racks is doubling. It's like the antithesis of Moore's law. So there has to be a better way. So what is a better way? Actually, it's not that difficult. If you look at the factors affecting computing, you can put together a formula for how to do it well. So the formula has 4 ingredients. You need to be innovative on memory. You need a lot of bandwidth, and you need good capacity to sustain that bandwidth. You need to be able to scale from an individual chip all the way to a higher level system. So you need efficient interconnects. You have to couple that with TOPS or FLOPS. That is still important. And you have to be able to do that not just for tensor operations, but for other things too. If that means you're going to go to lower precision, those still have to maintain accuracy. And finally, you need a software stack that can put everything together. Our adaptation of this formula is Corsair. Here is a block diagram of the Corsair chiplet. It's organized into a hierarchy of building blocks. The chiplet consists of 4 quadrants, quads, or gangs. Each gang, or quad, is an independent unit of computing. Inside each of the gangs, we have computational units, which we'll talk about, organized into cores and slices, along with memory, along with tensor reshaping, and a control processor. There are several elements that contribute to the efficiency and performance of Corsair. One of them, which Sid mentioned, is our approach to tensor cores. So we don't use traditional floating point tensor cores. Instead, we build our own SRAM-based in-memory computing accelerator, all digital. The benefit of doing this, dual bit serial integer computation, is that it gives the energy efficiency of integer computation while retaining the accuracy of floating points because it natively supports MX formats, or block floating points with a shared exponent. The second element is you can stamp many of these DIMC macros together into bigger and bigger building blocks. So this is a single 64 by 64 matrix multiplication unit, and it can perform a vector times 64 by 64 8-bit precision operations in 4 cycles. Half that time if you go to int4. So you put 8 of them together into an array, combine it with input, output, and weight buffers, and that becomes the basis of a core, a programmable core. 2 things to point out is that, as we said, there is operation beyond tensor operations, tensor operations. So we put a very high-performance SIMD core right next to where the output of the matrix multiplication sits. So that gives us fusion by default. And there is a large SRAM, on-chip SRAM, backing into each of the DIMCs. The DIMCs themselves are just 4 kilobytes, but they're backed by almost a megabyte of weight storage, which is the stash. That takes us to memory. Now, there are 3 types of memories. There is a weight storage, stash, which is a large on-chip SRAM for weights and caches. There is global memory, GM, which is, again, an on-chip memory for activations and intermediates. And then there is also LPDDR, which allows us to do less critical weights, less critical storage, prefix caching, system prompts, and other things. The 4th element is the interconnects. We took the approach of building things in a hierarchical manner. So we have a high-speed on-chip network, which connects the devices all-to-all manner. That extends to multiple chiplets inside of an MCM using die-to-die or DM link. That gets further extended to multiple MCMs over a PCI fabric inside of a server. That gets extended to as many nodes as we want, or as many servers as we want over Ethernet. So that's our approach to scalability. So putting it all together, what you see is the Corsair Accelerator, which is a custom-designed inference accelerator for data center inferencing of LLMs. This has the elements of in-memory computing, the DIMC, which provides 2,400 to 9,600 TOPS of dense compute at an industry-leading efficiency of over 38 TOPS per watt. All of that is done using native support for block floating point, or MX formats, which maintains accuracy, and I'll show you a sample of the output towards the end. Remember the two numbers, 4 terabytes per second and 4 picojoules per bit from NVIDIA. How about 150 terabytes per second and 0.3 picojoule per bit? That's the kind of efficiency we need to get a step function jump at addressing the biggest bottleneck of LLM computing. So that's the on-chip memory bandwidth aggregated for a card. How does this work? Does it actually translate to workloads? Let's take a look at a few of them. Let's start with something where we are just about reasonable. It's a compute-bound workload. It's a small clip width, and we are about 50 to 60% better compared to comparable GPUs. So all that preaching about 50, 60%, and it's meh result. Let's look at something better. How about, if you look at something which is actually memory-bound, this is where the bandwidth advantage starts to shine. Now, we are about a quarter of the latency and 4 times the throughput compared to both an H100 and a Blackwell. And that is also while we are sipping power, half the power almost of a B40. So that's where the advantage of performance and efficiency starts to show. Let's take it to the big league. What about an OSS 120B? So here is where the interactivity metric on the x-axis is almost untouchable by a GPU-based system. So we can get similar kind of throughput, but 10x, 15x higher interactivity per user. So at this point, the question is, OK, we have a formula. It seems to work. How about we just bake it into silicon and call it a day? No. One of the tenets that we talked about earlier was programmability. We want this chip not only to be performant, not only to be efficient, but highly programmable. And today, we will talk only about close-to-metal programmability. That is made possible by a device abstraction. There are many reasons for programmability. It comes from support for dynamic context, dynamic shapes, new types of operators, new variations in model architecture. So we need to support all of that. So we start out by a hardware abstraction through our instruction set. Everything that runs on Corsair device is expressible using the language of the ISA into a graph format. And the ISA is not a CPU binary. It's not an executable. It's actually a virtual ISA which is interpreted at runtime by every single gang independently. So imagine it's like running tiny little 32 VMs inside of one physical PCI card. How that happens is that there is a control cluster inside each of the gangs. So the PCI card has 32 such control clusters, each operating on their own ISA graph. The control cluster's job is to fetch the ISA graph, ISA instruction, interpret it, understand which hardware unit needs to be operated, generate a CSR, a hardware register CSR, deliver it to the hardware device, and wait for it to come back. The hardware device simply receives the instruction, executes it, and signals completion. All of this is fine-grained. There are no assumptions about timing. An instruction can take as long as it needs or as little as it needs. There is causal guarantee. There are no structural hazards. Everything is managed in a deterministic manner. And because we are able to target individual units, we can go down to a single DMA engine or a single DIMC, or we can trigger many, many of them at once. Because you have so much compute, and so little control programming needed to control the device, you have to be able to run things concurrently. So the very first thing that we are able to do is send a single ISA instruction to as many devices in a gang as we need. So you could trigger every single mappable DIMC, all 64 of them inside of a gang with a single instruction. But that's not enough. You can arrange 16 of them to be executed in any order concurrently by putting them into a dependency queue. It's only when you go to the next group of 16 ISA instructions that you have a serial dependency. But all those 16 instructions can be executed at once. If that's not all, there are 8 such queues. So you could have up to 128 ISA instructions in flight concurrently without any delay in between. Most of the times, we need only 1 or 2 queues. So if you find yourself running against that limit of 128, either you have very unique workloads, or you have some lazy programmers. Most of the time, it's the latter. There's another powerful concept that gets enabled because of our use of virtual ISA, which is support for dynamism. There are many applications for having dynamism in the compiled graph. It could affect the addresses of tensors, input-output tensors. You could program parameters, such as temperature, for every iteration without having to recompile the graph. Imagine like your assembly has variables that can be resolved at the decode unit of the hardware itself. That's what dynamic ISA enables. And to the right, there is a tiny excerpt of an ISA graph where there is a variable called job queue, and there is an RPN expression that resolves it at runtime at the time of graph execution. And because it's the deferred form of compilation, it allows us to enable applications such as dynamic context size. You compile the graph once. You don't need to perform compilation or regarded compilation for every change of context length per user. It's the single compilation of the graph gets resolved by the on-chip control cluster. Second is the expert routing. Traditional way of routing experts is to do it on the host. You generate the output from the attention module, take it through the gating function, and determine the number of experts and which experts on the host and route them. We can do it dynamically on the device. No need for recompilation, no need for host intervention. So why all this talk in a RISC-V conference? RISC-V is at the heart of our control core. Every single gang has a RISC-V cluster that performs all these operations. This is where the D-matrix ISA graph executes. This is where the assembly variables get resolved to allow dynamism for branch selection, for address resolutions. It allows us to operate in a decoupled manner in an asynchronous host fashion. And because we are an accelerator company and there is a lot of work for RISC-V to do, we built a tiny accelerator for the RISC-V, which is called Dispatch Engine, inside the control cluster. RISC-V, as Sid was saying, it's a phenomenal choice for accelerators. It's a modern, sleek, standardized ISA, yet extendable. And we have a variety of IP options from different vendors that offer different PPA targets and extensibility. For example, we've worked with Andes on our next generation RISC-V cluster using HVM. That customization allows us to make very specific optimization points inside of the design using the extensibility of the CPU. And there is a mature and evolving tool chain to support use of RISC-V. Looking ahead, we started out addressing the bottleneck of memory bandwidth using very large on-chip SRAM. Look, in our next generation, we retain the bandwidth advantage, but also obtain 10 times, 15 times more capacity by using DRAM instead of SRAM, but not in a traditional HBM manner. It's by using 3D die stacking of memory on logic or logic on memory. Looking ahead into the next generation, we'll go multi-stack to get even more bandwidth, even more capacity, and even more space on the logic die to put more compute on. There is also a RISC-V roadmap, as Sid briefly mentioned. We started out by putting just a scalar control core for Corsair. In the next generation, through our partners, Andes, we are going to use the RISC-V not only as a control core, but also as the vector processor using the RISC-V vector extensions and HVM. And we have more ideas on what to do after that. We said that AI is not a chip problem, but a systems problem. Today, we will not go into that topic. We will not talk about how we scale, how we play nice with heterogeneous systems together with GPUs. And we'll also skip details of our Aviator stack, which is the software, which doesn't require you to do close-to-metal programming. If all you want is a push-button solution, Aviator will do most of that lifting for you. And finally, it's not a guess anymore that inference computing on LLMs is the signature problem of computing today. It's the defining problem. It's an opportunity that an architect dreams about. The language models, which are behind the AI technology's evolution, have some unique properties. They have computational needs that require special hardware. They are important enough that people will take special hardware if you give it to them. And they're also not static, so your special hardware needs to evolve and be programmable and developer-friendly. With Corsair, we demonstrated that it is possible to create something which is performant, efficient, and programmable by a developer. So with that, let's work together in making AI technology more sustainable, putting it on a path to, or a trajectory to be more affordable and accessible to many more people. And thank you. I'll leave you with an excerpt of the output.